Hello and welcome to today's lesson. Today we shall be discussing implicit differentiation. We wish to answer the following two questions in today's lesson. 1. We wish to know why or when do we employ implicit differentiation? And secondly, we wish to know or learn how to differentiate implicitly. And of course, we shall end the lesson by demonstrating or by showing that in fact, when we differentiate implicitly or explicitly, we end up with the same answer. So let us proceed. Now, to answer the question why, let us consider these two functions written down here. The first one is y equal 3x squared plus 2x plus 1. And the second function is 3 equal 3x y cubed plus 2xy plus 4y squared plus x. In this first function, you observe that the left-hand side is a function of y, and the right-hand side, 3x squared plus 2x plus 1, is a function of x. That is to say that we can write this first function as y equal f of x. Y equal f of x, in the sense that the right hand side is a function that contains only the variable x. So y is equal to f of x. What do we say here? Since the right hand side of this equation is a function of x alone and not of x and y, we say that y is an explicit function of x. We say that y is equal to 3x squared plus 2x plus 1 is an explicit function of the variable what? X. And we write y equal to f of x. So going forward, whenever you see an equation that is written in the form y equal f of x, you know that this is written explicitly. Now let us move over to the second function. 3 equal 3x y cubed plus 2xy plus 4y squared plus x. The question is, can we write this function in the form y equal f of x? That is to say, can we write this function, can we express this function in this other form? What do we observe here? We observe that in this function, the right-hand side is a mixture of x and y. xy cubed plus 2xy plus 4y squared plus 4 plus x. So you observe that the right-hand side is actually a function of x and y. So if a function is expressed in this form, where the variables x and y are mixed on one side, we will now say that the function has been written implicitly. So the word implicit differentiation comes from the fact that the function you are about to differentiate has a mixture of two or more variables on one side of the equation, or maybe on both sides of the equation. The next question is it possible to make this equation explicit? Most times it is possible, other times it is not possible. Of course, where it is possible to rewrite your implicit equation as an explicit one, in that case, we can go ahead and differentiate explicitly. For example, if we have the equation x squared plus y equal to 3. The first question is this equation implicit or explicit? The answer is obvious. The left-hand side of the equation contains the variables x and y. So this equation here is implicit rather. But can it be made explicit? The answer is yes. So we can make y the subject of the equation by writing y equal to 3 minus x squared. In this way, we are written the function in the form y equal to f of x. So if a function is written in an explicit way and you differentiate, we'll now say that we are differentiating explicitly. However, if the function is written in an implicit way or in an implicit manner and you try to differentiate, we'll now say that we're differentiating what? Implicitly. Now that we know what an implicit function is and what an explicit function is, now that we can differentiate between implicit and explicit function, the next question we want to answer is, how do we differentiate implicitly? Now, just as we differentiate in explicit form, we'll differentiate each term of the equation. But this time, we'll have to be very careful when we are differentiating a function that contains y. For example, if we wish to differentiate x squared plus y squared equal to 1, the first question is it obvious that the differentiation here has to be implicit? The answer is yes, because the function on the left-hand side contains x and y. So let's assume that in this case, of course, we can make y the subject of the equation because the function is a simple one, but we won't be doing that. We choose to differentiate the function implicit. How? So we differentiate each term of the equation. So d dx of x squared plus d over dx of y squared is equal to d over dx of 1. So to differentiate, we differentiate each of the term with respect to what? With respect to x. But in this case, when you differentiate d dx of x squared, what do we have? We have 2x. That's okay. Plus, when it comes here, to differentiate d dx of the function y squared, we have to be very careful. At this point, we must apply what we call the chain rule. Now, we check the description below to get a link to chain rule so that you recall what chain rule is. Now, let us apply chain rule in this differentiation and see what happens. To differentiate this function using chain rule, we say, okay, let u be the function inside y squared. So if u becomes y squared, then what we have here becomes du over what? Over dx. So in fact, we are trying to differentiate du dx if u becomes y squared. Coming back here, so if u is y squared, what will be our du over dy? Our du dy is nothing but what? 2y. Okay, 2y. What are we looking for? We want to find a value of du dx. So du dx is nothing but du dy, du over dy. Now, what do we multiply by du dy to get du dx? If you recall our chain rule, you see that du dy times dy over dx. How? If you multiply du dy by dy dx, dy and dy will cancel off, and what we have left is du by dx, which is what we're looking for. So du dx will be nothing but du dy, which is 2y times dy dx times dy over dx. And the final answer there is 2y dy over dx. So what do we see? So to differentiate this function y squared in an implicit function, this will give you 2y times what? Dy over dx. So this gives us 2y dy dx. So the comment I wish to make here is this. When you differentiate implicit or when you differentiate implicitly, whenever you differentiate a function that contains y, you differentiate it as you do for x, except that whenever the function contains y, you must multiply the derivative of that function by what? Dy dx, because of what we have just seen here. Equal to, this is constant, and we differentiate the constant, what do we get? We get 0. We'll stop there for now, because we just want to know how to differentiate implicitly. So, to clarify what we're saying further, if we have another function, say y cubed plus 2y cubed plus 6, and you want to differentiate implicitly. So when you differentiate this function, you get what? 2x squared. When you differentiate this function, what do you get? I'd like you to pause the video and check what you get. So if you go by the chain rule, this will be nothing but, if you differentiate 2y cubed, this will give you 6y squared. But since it's a function of y, you must multiply the derivative by what? dy over dx. This is a constant that will give you 0 equal to 0. So this is how we differentiate implicitly. The last thing we want to show in this lesson is that whenever we differentiate implicitly or explicitly, we end up with the same solution, where it is possible to simplify the implicit function in terms of an explicit one. For example, if we have the function xy equal to 2, yes, the left-hand side is a function of x and y. So we should do what we call implicit differentiation here. However, it is possible here to separate the variable x from y. So let us proceed. If we divide both sides by x, we end up with what? Y equal to 2 over x, which you can also write as 2x raised by minus 1 by indices. So what do we see here? The function xy, which was implicit initially, has become explicit, y equal to 2x raised by minus 1. So we can write this as what? Y equal to f of x. So this becomes explicit. So let's differentiate this explicit function and see what we get. So dy over dx is equal to, differentiate this, what do we get? We get minus 1 times 2 power rho minus 2x minus 1, right? So this gives us minus 2x raised by minus 1, 2. Or we can write as minus 2 divided by x squared. So if we differentiate explicitly, that is what we get. We get that dy dx is equal to minus 2 over x squared. Let us quickly differentiate the function implicitly and see what we get. So again, we differentiate xy equal to 2. But this time, we choose to differentiate implicitly, the way it should have been. Now you observe that the left-hand side is a product of two functions, x and y. So we shall also apply the product rule of differentiation, and I hope you recall what it is. We know that y equal to uv. By product rule, we say that dy over dx is equal to u v prime plus what? V u prime. We keep the first function, differentiate the second, plus keep the second function, differentiate the first. There will also be a division below, a link below the description box to check what product rule is. Now let's go ahead and differentiate implicitly. So we differentiate the left hand side with respect to x with xy, plus the right hand side with respect to x, which is 2. Let's proceed. This is a product. So our u here is the first function, which is x, and our v, the second function, which is what? Y. We proceed. So we keep u, so u here is x, u is x, and we differentiate v, so v is y. So when we differentiate y, what do we get? We get 1, right? We get 1. But recall that since this is a function of y, what do we multiply with? We multiply the derivative by what? dy over dx. Plus v, we keep v is y, we keep y, then u prime, we differentiate u, and u is x. When we differentiate x, what do we get? We get 1 equal to the right hand side. 2 is just a constant, and when we differentiate a constant, we get what? 0. So what does this give us? So this gives us x dy over dx plus y equal to 0. And what we want is dy dx. So we make dy dx the subject of the equation. And this gives us what? This gives us x dy over dx is equal to, plus y becomes negative y on the right hand side. If we divide both sides by x, what do we end up with? We now see that dy over dx is nothing but what? Minus y over x. The question is, now when we did explicit, we got negative 2 over x squared. Now implicit gives us negative y over x. Are they the same? The answer is yes. How? Now, in the explicit form, we had that y is equal to 2x raised to the power minus what? 1. So if we put that value here for y, what do we get? We get minus, what is y? y is 2x raised to the power minus 1. So y is 2x raised to the power what? Minus 1 divided by what? X. If you simplify this carefully, what do we get? This becomes minus 2 over x squared, which is just the same thing as what we got when we did our explicit differentiation. So this tells us that where it is possible to simplify the implicit function in terms of explicit and differentiate, we end up with the same solution. In our next lecture or our next video, we shall be taking more examples on implicit differentiation. So if you like this video, then hit on the like button, subscribe to this YouTube channel, and make comment where you feel necessary. So see you in the next